Hi everyone. So just to let you know, I started you off muted. If you have a question at any moment, feel free to unmute yourself and add to your question. So you can ask your question. I just muted you because I know there has been issues with people being Zoom bombed. So I just wanted to be extra careful. If at any moment anyone's being rude or disruptive, either in the chats or in the Zoom meeting, feel free to let me know so I can bump them out. All right. So hopefully you're doing well. It's a very cloudy day. Let's go ahead and begin our lecture. I see more people joining our class. That's good to see. All right, so this is being recorded, unlike last time where I had a mistake where I didn't record. I'm so sorry about that. It's being recorded. It takes about an hour or two for it to load. So up until then, once it's ready, I'll post it onto Canvas. All right, let's go ahead and begin our lecture.
Can you do some homework problems?
Yeah. What homework questions do you have?
On 4.4, number 14.
4.4, number 14. All right, I'm going to share my screen so you can go ahead and do that problem. Are there any other homework problems? 4.414. Anything else?
Can you also do number on 4.3, number 7, C?
Yeah. All right, let's take a look at those. If you have a question, it's another point. Feel free to chime in.
May we also do 4.3, number 6?
All right, and 6. All righty. So let's take a look at your homework. So 4.3. Start with 4.3. 4.3, number 14.
Uh, 4.4, sorry.
4.4?
Yeah.
So I'll start with 4.3, just because it comes before 4.4. So 4.3, number 7 and 6. So 6 is right here. So I want to graph this function. And don't let this E fool you. You know it's still supposed to look like this, right? It's still an exponential function. But if I know what shifts we have, then I can anticipate what's going on. So this lets me know it's going to shift to the right 3 units. This negative lets me know it's reflected around the x-axis. So meaning instead of looking like this, it's not going to look like that. Our graph is going to look like this. And this affects our horizontal asymptote, right? It kind of flips it. So let's solve for 0 to see where that is. So 2 minus x is equal to 0, minus 2 minus 2. Negative x is equal to negative 2. Negative 2. So x is equal to 2. So our asymptote will be at, I'm sorry, I'm confusing it with logarithmic, right? So this is just going to cause a horizontal shift. That just causes a horizontal shift because for exponentials, we look at this for our vertical asymptote, horizontal asymptote. So we have a horizontal asymptote at x is equal to 3. So we have a horizontal asymptote there. But regardless, if you start plotting points, you'll see what you should be working with. All right, so I'm going to erase my notes above so you can start creating a chart. Okay, so I'm working with exponents, and I want to keep in mind that e to the 0 is 1, and e to the first power is e. And the reason I want to keep this in mind is because I want to make that exponent 0 and then 1, because I'll make it easier when I'm working on the chart. And have your calculator handy, because e is like pi. It's an irrational repeating decimal. All right, so to get 0 there, I will have to plug in a 2, right? So if I plug in a 2, I'm left with -2 times e raised to the 2 minus 2 plus 3. The exponent of 2 minus 2 gives a 0, so we're left with -2 times e to the 0 plus 3. A number raised to an exponent of 0 is 1, so we're left with -2 times 1 plus 3. So that just gives us 1. So I have the coordinate point 2, comma 1. Let's plot that 2, comma 1 is right here. All right, now let's make that exponent to be 1. To get 1, I would want to make 2 minus 1, because I'll make my exponent 1. So let's make x be 1. So I have -2 times e raised to the 2 minus 1, because x is 1, plus 3. So I'm left with -2 times e to the first power plus 3. All right, I have to find a calculator to get a decimal answer. So I have e to the first power times -2 plus 3. If I round to the nearest tenth, I would have 2.43, so 4, which gives me the point 1 and 2.4. So I have 1 and 2.4, so something like this. All right, so we're going to have 1 point going towards our asymptote forever to infinity.
You get
Another one going
-2.4?
When I worked it out, oh, it's -2.4. My calculator said that, but I didn't listen to the calculator. -2.4. So I have 1 and -2.4, so 2.5. That's 1 and -2.4. Thank you. So we have one going towards our asymptote and the other one pulling away. So this gives us our exponential function. Alrighty, let's take a look at, that was 6, now 7C. Calculate the ending balance for each of the following accounts. We have 4,700 at 3.5% for 6 years compounded daily. All right, so can someone please remind me of the formula? I have A is equal to P with 1 plus, and then the rest I forget. I think it's N times T, right?
R over N.
Okay, cool. Thank you so much. This is a formula that I always forget because we have it in our book, so we can always refer to it then. So let's make it a point to find each one of those pieces. Let's find P, let's find R, let's find N, and let's find T. And it's a matter of just inputting into our calculator. So our P is the starting amount, which is 4,700, 4,700. Our R is our percent, so I have 3.5%. Make sure to change it to a decimal. Move decimal over to the left 2, so it's 0.035. Your n is how many times it compounded. So like quarterly, monthly. Here we have daily. So this lets us know that n is 365. And t is for time, and it's always in years. So we have 6 years. All right, once we have everything sorted out, let's go ahead and input it into our function. So I have a is equal to p, 4,700 times 1 plus r 0.035 divided by n, 365, and times t. 365 times 6. All right, let's do this in pieces. So I have 4,700. All right, so I have 0.035 divided by 365 plus 1. That's about 1.000. Keep that in your calculator. And then you can raise it to 365 times 6, 2190. All right, so let me do that again. 0.035 divided by 365 plus 1. I'm going to raise it to an exponent of 2190 and then multiply it by 4,700. So your answer is 5798.2285, and it continues on. But because we're working with money, we want 2 decimals. So we want 5798.23. So our answer is 5,798.23. I think the tricky part here was a daily, right? Any questions about 7B? Oh, yes, for 7C. I'm so sorry. I am so sorry. Okay.
Okay, it helps too.
It helps too. I am so sorry. I looked at it, but I totally did the wrong one. All right, see. The big thing here, and what makes this different from the previous one, is continuously. So this one, I know it as A equals per. A is equal to P, base of E raised to the exponent of R and T. Continuously mean it's not, you're not finding the interest and adding it on every day as daily or every month as monthly. You're doing it consistently, never ending. It still is all very close to daily. All right, so again, we want to figure out our things. P, R, and T. All right, our principal, our starting amount is 4,700. Our rate is 3.5%. Remember the decimal over twice. So we're really going to work with 0.035. That's the number we want. And time is in years, 6 years. Let's go ahead and input that. A is equal to P, which is 4,700. E raised to the R times T. So I'm going to multiply 0.035 by 6. So let's multiply that first. 0.035 times 6. So far I have 4,700 with the base of E raised to the 0.21. Okay, let's go ahead and figure that out. So use your calculator to work with E and make that exponent 0.21. Then multiply it by 4,700. And your answer is 5,798.286882. But because we're working with money, we want 2 decimal places. So 5,798 and 20. So we want the 10th place, we look the next one to know if we round up or we keep. In this case, we round up because it's over 5. So we will have 9. That is 7C. All right, moving forward to 4.4, number 14. Graph the following logarithmic function and find the domain and label the vertical asymptote. Find the 2 points of each graph. All right, and here is kind of where I twisted. How's the expression? You something or wires? I don't know. So for exponential functions are, so let's make a list. Exponential functions are graphs tend to look like this. For our log functions, our graphs look like that. And of course, we can reflect them over. We can move them up or down. That part in parentheses tells our vertical asymptote. So for exponential functions, we have a horizontal asymptote. For logarithmic functions, we have the vertical asymptote. We solve to 0 to see where it goes to. So x might, or we look at the shift. So here we know it's moved to the right 1. I know it's a minus, but remember when it's in parentheses, it's the opposite. So our vertical asymptote will be here at the line x equals 1. All right, let's go ahead and graph our logarithmic functions. So let me erase these little notes that we have. Now I want to keep the same, similar to when we did exponential functions, I want to keep some numbers in mind. I know that 4 to the 0 power gives me 1. 4 to the first power gives me 4. And 4 squared gives me 16. And 4 to negative 1 power gives me 1 over 4. And I want to keep these in mind because I want to make this either be a 1, I want to make that a 4, and I ideally don't want to make it a 16 because that doesn't fit on my chart. So I want that to be a 1 or a 4. Okay, let's do our chart, keeping that in mind. So what should I make x be so that it is, so that we get a number like this? The answer, 1, 4, 16 might be too big. But you can even test 16 if you want more points, just to verify. So what should x be so it can be 1? X should be 2. Yeah, thank you. X should be 2. So I have log base 4 of 2 minus 1 plus 2. Okay, 2 minus 1 gives us 1. So log base 4 of 1 plus 2. Now, the reason we do this is because we're thinking. Let's write this as the exponent. Log base 4 of 1 is equal to what? It means what? 4 to the x power equals 1. So therefore, my answer to log base 4 of 1 can only be 0. Because didn't we just say that 4 to the 0 power is 1? In the top right, or when we had our little idea of how we're going to work this out. So 4 to the 0 power is 1. So this part of log base 4 of 1 is 0. So I have 0 plus 2, which gives me 2. So I have the point 2, comma 2. 2 up 2 is right here. 2, comma 2. All right, let's do this again. Now let's make it so that let's work with this one. Let's make it so that we get a 4 in the parentheses. Let's make it so that we have a 4 in the parentheses. So 5 minus 1 is 4, right? 5 minus 1 is 4. Let's make x 5. So x will be 5. So that we have log base 4 of 5 minus 1 plus 2. Okay, so 5 minus 1 is 4. So I have log base 4 of 4. So what we're thinking is 4 to the what power gives us 4. So when we evaluate this part right here, we get 1. So I'm left with 1 plus 2, which is just 3. So I have the point 5, comma 3. So that's 1, 2, 3, 4, 5, and I go up 3. 1, 2, 3. I have this point right here. So one side is going to go towards the asymptote, and the other one's going to pull away. And that is our graph. All right. Let's move on with today's lecture.
Thank you.
You're welcome. Thank you for asking. I totally forget to ask if anyone has homework questions, so thank you for reminding me. All right, exponent rules. So before we start any college algebra content, it's really helpful just to have a refresher as to how exponent rules work, because it'll make things easier to work with if we have these ideas in mind, because they're so easy to overlook. So multiplication rule. It says if I have the same base, see how we have an A and A, instead of evaluating and then multiplying it out, I can cheat by adding the exponents. So a brief example is if I have 2 to the first power times 2 to the fourth power. Instead of punching each one on my calculator separately and then multiplying it, I can save some work by finding the exponent of what my answer would be. So because I have the same base of 2, I just add 1 plus 4. So my answer is 2 to the fifth power, and that saves them some work. So I can just do 2 raised to the fifth power, which would give us 32. Now I have a division rule that also works if I have the same base. If I'm dividing and I have the same base, I'm going to subtract. Now I wrote this rule twice because we can have division written horizontally, or we can write it as a ratio. So regardless, I'm going to subtract the first minus the second, or the top minus the first. So if I have 3 to the fifth power over 3 to the fourth power. Yeah, I can figure out what 3 to the fifth power is and divide it by 3 to the fourth power. But according to my rule, I can just subtract the exponents. So 5 minus 4, which gives me 1. So it's 3 to the first power, which is just 3. Next rule, power of a power rule. So this is saying if I have an exponent being raised to another exponent using parentheses, they're multiplying. So if I have 5 squared being raised to the third power, that would have the same effect as 5 with the exponent of 2 times 3. So 2 times 3 gives us 6. That would be our same answer. Now, please note, be very careful with multiplication rule and power of a power rule. Be careful. I often see students confuse those two. You need to have a parentheses. The parentheses is very important for us to use that power of a power rule. Okay, another helpful exponent rule is power of a fraction rule. So this saying, if I have an exponent and I have it applying to a fraction, it applies to the numerator and applies to the denominator, so that each one has the exponent applied to it. So for example, if I have 2 over 3 to the third power, I don't have to multiply the fraction 2 over 3 times 2 over 3 times 2 over 3 times. I can just apply the exponent to each one separately. So I have 2 cubed divided by 3 cubed. The exponent applies to each one. And my favorite, a number raised to 0 power is 1. And we've seen that how 2 to the 0 power is 1, 4 to the 0 power is 1. One we also worked with is negative exponent. And this is saying that if I have an exponent that is negative, I can undo it by writing as 1 over. So if I have 5 raised to negative 1, the same thing as 1 over 5. Not to be confused with if I have 1 over 5 raised to negative 1 powered. If it's a fraction, then we flip it. So it'd be 5 over 1 raised to the first power. Raised to the first power. That just undoes a negative. Now, when it's a whole number, the reason this is so is because you're essentially also flipping the fraction. But we have a whole number of 5. So it'd be 5 over 1, and you flip that. Next one, fractional exponent. And what this is, and we've seen this one before, is any exponent that's a fraction is really a radical. So if I have 2 raised to, let me choose another number. If I have 4 raised to the 2/3 power as a fraction, it's the same thing as writing the cube root of 4 squared, where the number on the top on the numerator is your exponent, and the number on the bottom is your radical, your index. It's called index. So you can follow and see where each number went. And 4 is your base, that's a number, and your radical. Okay, so these are all of your exponent rules. And I kind of try to work in an example. The most important one that you'll see in the next upcoming section is the multiplication rule for sure, the power to a power rule. We'll see those a lot. So keep those in mind. Okay, let's go on with today's lecture. So today we're covering 4.5. And if you see your updated schedule, it says we're pretty much covering a section per day. All right, so let's go on with today's notes, 4.5. Now let me know how you think of the lecture going on. My initial plan was to erase all of the work that's done and then creating skeleton notes that we fill in together. But I know writing takes time and we all write at different speeds. So I think it's nice that the work is written there for us so we don't get caught up on writing and we don't fall behind. But let me know, I'm open to ideas. So let's begin our new section, 4.5, properties of logarithms. Our objectives are 1, basic properties of logarithms, 2, product rule, 3, quotient rule, and 4, product to a power rule. I'm sorry, product rule. Power rule. Basic properties of logarithms. We have already introduced logarithms as the inverses of exponentials, learn how to evaluate logarithms, and establish how to convert logarithms to their exponential form using the definition. So this is just telling us how we can go from log form to exponential and exponential to log form. It's just a matter of how to work with it. Whenever I have anything in log form, I always make it a point to rewrite it as an exponential form. Okay. We now need to investigate the properties of logarithms. We will start with 4 basic properties of logarithms. Property 1, log base b of 1 equals 0. And if you rewrite it to exponential form, you can see that it's because if we have b to the 0 power, our answer is 1 because we said any number to an exponent of 0 is equal to 1. Our second rule, log base b of b equals 1. And if you write to exponential form, it's easy to see. We have it there. B to the first power is equal to b. And if you don't, you can think about it. B raised to the first power. Well, a number raised to the first power is just itself. So it has to be b. And 2 things to keep in mind. Log of 10 equals 1. And ln of b equals 1. And this is because if I don't have a log written, I assume log base 10. So this is log base 10 of 10. That would equal 1. And ln of v is equal to 1 because ln of v is log base e. And log base e of e, that would be 1. Another trick to think about it is if they have the same base, log base and number, they're going to be 1, just like here and here. Same thing if I were to have log base 4 of 4. Without writing an exponential form, I know my answer should be 1. Moving forward, for the next two basic properties of logarithms, we need to recall that f of x is equal to b of x, and g of x is equal to log base b of x. And they're inverses of each other. That's what we need to recall, that they're inverses. And for any two inverses, we know composition of each will give us x. So this is the haunting part of an exam that you last took, right? We showed that a function composed by its inverse should give us x, right? So if f is an exponential and g is your logs, when we do composition of them, our answer should be x. And this leads us to another property. So property 3 says if I have the same base and a number, if I have a number raised to an exponent, that's going to be a result. So the same idea as if these things being 1. Though that is not proper to say. Same thing if I have a base raised to a logarithm. If it has the same base as your exponential base, they're also inverses, they're mathematical inverses. So they make 1. Again, it's not proper to say that. We say that that happens because they're inverses. So it'd be helpful to say this holds true because they're inverses of one another. So a log base and an exponential base, they're inverses. An exponential base and a log base, if it's the same number, they're they're inverses. So they undo each other. Example 1. Simplify the following expressions using the 4 basic properties above. All right, so this should be done so that you can easily identify things without having too much thought with it, if you remember the properties. So let's take a look at A. Log of 1. All right, so remember there's a base. So if you want to think about it a bit more, 10 to what power gives me 1? So this is using property 1. Therefore, log of 1 is equal to, well, 10 to what power gives us 1? It has to be 0. My answer is 0. For the next ones, remember that we have a log base and a number. They make 1, right? So our property is property 2. So that log base 5 of 5 is 1. C uses property 3. Remember, this is the same thing as log base e of e, raised to the 4th power. So these are gone. They essentially make, I don't think it's correct to say they make 1. And so our answer would be our exponent, which is 4. For D, our answer is just x. For E, the log and the exponent both have a base of 10, so our answer is x plus 1. And you'll see these answers right here. So our properties are hopefully going to make things easier for us. The three most important properties of logarithms are called the product, the quotient, and power rules. These logarithmic functions are the inverses of exponential functions, and these properties will mirror the product, the quotient, and the power rules of exponents. So first is our power rule. So they're kind of like the opposite of the exponential rules we learned. So the product rule, we call product rule for exponents. If I have a number raised to an exponent and I have the same base raised to another exponent, then I can add the exponents. Well, it works a different opposite way. So if I'm adding, I can write it using multiplication, because now we have logs, and logs are the opposite. So this is your product rule. Your product rule reads log base b of x plus log base b of y equals log base b of x plus y. So let's take a look at example 2. Use the product rule to write the following expressions as a single logarithm. So log of 3 plus log of 5. Okay, so they have the same log base. Remember, if a number isn't written, we assume 10. And that's the only condition needs to hold true. If I have the same log base, I can rewrite it with 1 log. So because it's being added, I can rewrite it using multiplication, as we see on the next line. So this can be rewritten as log of 3 times 5, which is 15. That's example A. Let's continue with example B. ln of x plus ln of x plus 1. So because we have an ln and the base isn't written, so we assume it's base e. Because it's being added, I can rewrite it as multiplication with only 1 L. So instead of using 2 L's, I use 1 L. So I have ln of x times x minus 1. And then I'm forced to do some distribution. So x times x times negative 1. We're left with x squared minus x. ln of x squared minus x. And because, so take a quick look at your product rule that's highlighted. Because I have an equal sign, this means I can compress it with 1 log, or I can expand it. Because it has an equal sign, I can move from left to right or right to left. Let's take a look at example 3. Use the product rule to write log base 3 of x squared times the square root of x plus 2 as the sum of 2 logarithms. Okay, so here I want me to add. It wants me to work with a log and then plus another log. So how can we do that? Well, again, we have our product rule. I can take 1 log and work it to 2 logs if they're being multiplied. So here, even though it's not written, I assume that x squared is being multiplied by that square root of x plus 2. So starting from here, I can take this one as 1 log and then take this other one to be another log, and I can write them using a plus like we do right next to it. I have log base 3 of x squared plus log base 3 of square root of x plus 2. And therefore, I have rewritten it using 2 logs. So that would be my answer. Now, these can be very confusing to work with, but they do require a lot of practice. So make sure you do your homework. Next, we have a quotient rule. So first was our product rule. Second, we have our quotient rule. Our quotient rule is if I have 2 logs with a minus, I can rewrite it with 1 log using division. And it's always going to be your first divided by your second. Okay, let's take a look at example 4. Using the quotient rule to write the following expression as a single logarithm. Okay, so we have the same log base, beautiful. Now this minus is telling me that I can use my laws of logs particularly the quotient rule. So I can write it with one log base 2, and I'm going to take my first one, which is x, and divide it by my second one, which is 3. And this would be my answer, which we have written. Same thing for b. I have the same log and same base. Because I have subtraction, I can rewrite it with one log, as we see below. So I have log of our first, which is x, divided by our second. The second is the whole thing, x plus 2, divided by x plus 2. Now remember, I can use these both ways. So I can use it to condense to one log, or I can use it to expand it to use several logs. Let's take a look at example 5. Use your product and quotient rules to write log base 4 of x times y over z as the sum and difference of logarithms. So in other words, it wants you to completely expand. Write it with as many logs, just try to make it as long, as lengthy as possible. All right, first thing you want to work with is that division. You want to break up that division. So it's always your top minus your bottom, or first minus the second. So I have x, well, we keep the same log in log base. So log base 4 of x times y minus our bottom, log base 4 of z. And you want to bring along the log base 4. That's a common mistake I see. You forget to write that log as we're expanding. Okay, so even though it's not written, we know that x and y is being multiplied, right? So because it's being multiplied, I can use my product rule for logs. So I can write this as a plus using 2 logs, right? Just as we have right here. Log base 4 of x plus log base 4 of y. And then I still have to finish what we've done so far. Minus log base 4 of z. All right, taking a look at these problems, what was it, 2 through 5? Are there any questions of any one of these in this page before we move forward? We've gone over the product rule and the quotient rule.
No.
All righty. Let's move on to the third rule. And this is the last of our rules, the product rule. Power rule. Power rule. This one's really weird, but again, they're all weird. So the power rule says if I have an exponent, I can go ahead and rewrite it as a number that's being multiplied to your log. But this number, we're going to write it in the front. So you see this exponent? I'm moving it to the front. So I have times whatever it is. And we see that right here. So an exponent doesn't have to have the job of an exponent. It can have the job as multiplication. So maybe I'll leave that little drawing there. You can take your exponent and move it forward. So exponent can be multiplication, if that helps. All right, take a look at example 6. Apply the power rule to rewrite the following as an equivalent expression. All right, so all I want you to do is work with that exponent and rewrite it. So here my exponent is x plus 1. I'm going to take that whole thing. If it's more than one number, if it's plus or minus something else, use parentheses. So I'm going to take that x plus 1 and move it to the front, just like we have here. X plus 1 times log 2. All right, ln of square root of 5. So remember our rules of exponents. If I have a radical, it's a fraction in disguise. So this is ln of 5 to the 1/2 power. Okay, just like before, I want to take my exponent and I want to move it forward. It has all of that written right here. We have ln of 5 to the 1/2 power, and I take my exponent and move it forward. So I have 1/2 times ln of 5. And see, it just wants you to rewrite it. So if I have it as a number in front, as a multiplication, I can rewrite it to be my exponent. So it can be log base 4 of x squared instead of being 2 times log base 4 of x. And you can use it interchangeably depending on what you're being asked to do or what your question is requiring. Let's continue forward. The remaining portion of this section will be 2 separate examples that will help commit the properties of logarithms to memory. So if it's helpful, when you have some time before you start your homework, make sure you write down these 3 rules. Write down your power rule, write down a little piece of paper or post-it. Write down your quotient rule, and write down your product rule. Write down a note card or a flashcard, or just a little paper, a little square of paper, because you're going to see them a lot. And if you have them handy just next to you, it makes it easier to work with. Let's take a look at example 7. For the properties of logarithms, to write each logarithm as a sum or a difference of multiple logarithms. Okay, so it's asking us to expand as much as possible. Whenever we see division, we think subtraction. So to write this as subtraction using 2 logs, I'm going to subtract the top minus the bottom. So we have that here, ln of y squared minus ln of x times z. We're almost done. I see I have an exponent, and I can move it to the front. So I have to use my power rule. And I see that x times z, they're being multiplied. So I know this will give me my product rule. Meaning, if they're being multiplied, I can write it with 2 logs with a plus in between. So if I write this, I have 2 times ln of y minus. Now this whole thing's being subtracted, so I have to be very careful. It's subtracting the whole thing. So let's write some brackets. Ln of x plus ln of z. Now I must be careful and distribute that minus sign, so I can drop my brackets. So lastly, my answer will be 2 ln of y, distribute that negative, so we have ln of x minus ln of z. Let's take a look at B. All right, so I want to rewrite it and I want to expand as much as possible. I see this 3, so I know I should move that forward to multiplication. And because we see this division, I know that it has to be a minus. Okay, so it first starts off by treating that exponent as a number that's being multiplied. So cool, that helps us take it step by step. And now I'm going to work with that division. I'm going to use that subtraction. So I know we'll have x square root of y log minus c to the 4th power. As we see in the next line, log base b of x square root of y minus log base b of z to the 4th power. All right. Now, we're not careful. Every multiplication should be using a product rule, so let's write it with a plus. So I'm going to take this here and write it using a plus with 2 logs, like we have here. Log base b of x plus log base b of square root of y. And we write, bring down everything you've done so far. Okay, now you see this square root? Remember, square root is the exponent of 1/2. So I can now bring my exponents forward. So I can bring the 1/2, bring it forward to that log, take that 4 and bring it forward to that log. All right, so in brackets, I have log base b of x plus 1/2 log base b of y and 4 times log base b of z. Lastly, I want to incorporate that 3. So I want to distribute that 3 to each term. So 3 log base b of x, and then 3 times 1/2. Let's do that work on the side. 3 times 1/2, write a 1 over 3, and multiply across. 3 times 1 is 3, 1 times 2 is 2. I have 3 over 2. So I have 3 over 2 log base b of y, and 3 times 4, we have 12 log base b of z. This one was a lot of work. It's very challenging, but just take it one step at a time. Now we can use our laws of logs to expand our logarithms, but we can also use them to condense and write them as one log, as we'll see in example 8. Use the properties of logarithms to write each expression as a single logarithm. Well, my advice is work with those numbers that are being multiplied on the front. Make those exponents so that you don't have numbers to worry about. So that's going to be my new exponent. 4 is going to be my new exponent. All right. So I have log base 5 of x squared minus log base 5 of y. And now my 4 is an exponent. Log base 5 of 4 to the 4th power. Subtraction is the one that will give you the most trouble, potentially. So deal with subtraction first. So I'm going to subtract this, meaning I'll divide it to one log. So I have log base 5 of x squared divided by my y. And lastly, bring down what you have. I still have that plus log base 5 of 0 to the 4th power to work with. All right, because I have addition, I must rewrite this using multiplication. Multiply the numbers that don't have the log. So x squared y times 0 to the 4th power, just as we have right here. Now, if it's helpful, whenever you have a number and you're multiplying with a fraction, always write it as over 1. So x squared times 0 to the 4th power like we have here, and y times 1 is just y like we have here. All right, I have succeeded and I wrote it using one log. And this is possible because they're same log and log base. If they don't have the same log base, then I can't do this. So they all have the log base of 5. Taking a look at B. Okay, so I want to condense it using one log. So I see a plus, so you might think, hey, I can use product rule. Well, no, in order for me to use product rule, I would have to have log here too, and I don't. So what I can do is I can work with those exponents. I can take that 1/2 and make it my exponent. I can take that 3 and make it my exponent. That's helpful. So I now have log of x plus 1 raised to the 1/2 power minus log z cubed. And then the subtraction, and I have 2 logs of the same base. I can rewrite it using division. So I have log of x plus 1 to the 1/2 power divided by divided by z cubed. And lastly, we don't like to keep our exponents as fractions. So whenever possible, write it as square root or cube root or whatever. So this would be square root of x plus 1. And that's it for today's lecture. So before we leave, let's make a safe space where we have all of our laws of logs. That's what I've often seen it called, laws of logs. And we have them written, right, in our notes. So let's take back and take a moment to remember our 2 laws of logs. We have our product rule, something that looks like a quotient, and then exponent. Let's take a look back. So first we had our product rule. And this is if I have the same log base with a plus, I can write those 2 numbers that are our logs and I can multiply them together, right? So let's take the time to write that down. So I have product rule, which is log base b of x plus, you make that another color because it's important, plus log base b of y is the same as log base b of x times y. All right, let's remember that quotient rule. That's the one that deals with subtraction and division. Our second rule was quotient rule, and that says log base b of x minus log base b of y is equal log base b over first divided by second. So x divided by y. So very similar, but instead we have a minus. So I have log base b of x minus log base b of y equals, I can write it with one log base b of the first, which is x, divided by my second, which is y. It's my quotient rule. Third one, our exponent rule. Our exponent rule is, I'm sorry, it's called the power rule. The power rule is if I can move, well, it says I can move my exponent and treat it like a number that's being multiplied. So I have log base b of x and t. So log base b of x with the exponent of t, that will equal t times log base b of x. And that was called the power rule, right? All right, so I just want to summarize what we learned for this section, which is the laws of your logarithms and how we apply them. So remember, because it is an equal sign, this means I can work from left to right, or I can work from right to left, depending if it's asking to expand or write as one log. All right, I hear a microphone on. Is there a question? All right, before moving forward, are there any questions for today's lesson? And that's okay. You can save your questions for our next class meeting. I'll be happy to help you then. Make sure you bring some questions, either try your homework, or if you're looking over your notes from our lecture and you came up with something that sounded funny, feel free to bring those questions in. I'll be happy to help. Alrighty. Andrew, do you have an announcement for us, or is there anything you would like to share?
Yeah, so we got an SI session after class today, and since it's 6 o'clock right now, then we'll just start it at 6:15. So it'll take like a 10-minute break. Everyone can go get a drink or whatever, and then
To the fridge.
yeah, go to the fridge, get something real quick. But and then today we're gonna be going over some stuff from last week, like the interest rates. We're gonna be going over that, and then Wednesday before class we're gonna be hitting on the logs a lot because this stuff is pretty confusing and yeah, and it's good to get a good handle on it because we're gonna be going deeper into it soon. So
yeah.
please
And
come.
if you have time under class, you know, I know maybe you feel like, oh, we can't do quizzes. These quizzes, I use programs so they're randomized. So if you ever have time, want to go over those quizzes, take a look at those instructions, feel free to do so. But again, do whatever you want. But yeah, you're very right. These problems require a lot of practice. They might seem easy when someone else is doing them, but then the moment you try doing them, you're like, oh my gosh, what are we doing?
Yeah.
Everything's so confusing. So make it a point to, you know, do your homework, come to questions either our Wednesday class or Monday class, and go to your SI session. You're already logged in Zoom, so I encourage it.
Yeah.
The link to join the Zoom for the SI session, you will send it to our email or?
Oh, let me send it. I'll send in the chat right now. Thank you for that. There, it's in the chat, and then also it's on the Canvas in your inbox. So I don't know if everyone can get to that, but it's on when you go into the Canvas on the left side. It says inbox, and so click on that, and I'll be sending them before every time.
Okay, cool. Thanks.
Yeah, you got it. All right, so 6:15.
Oh no,
10
before
minutes.
class, I won't give you too much time before. All right,
Yeah.
I won't give you guys too much time between the Zoom link and class because there's been a lot of Zoom bombing going around. All right, so that's it for today. Have a nice day. Try your homework. Enjoy your essay lecture. Bye-bye.